Okay, let's start with the last panel in the conference. I know it has been very heavy 4 days, but we still have few sessions to do. And this is a very interesting panel, at least to me, and those to do energy system analysis, energy planning, integrated assessment models, or are interested in mitigation in general. We have here 5 panelists. Here is with us Shir Kilkish, who is the Vice Chair of Working Group 3 of IPCC. We have Henrik Lund, who is professor in University of Aalborg, but is also a creator of Energy Plan model. That is one of the first models who started to think about how to increase the penetration of variable renewables in a cheap way. Then we have Felipe Feijó from Pontificia Universidad Católica de Valparaíso. He is an energy planner who has experience in GCAM, so integrated assessment model, but also he built, together with our group in Zagreb, energy system analysis model H2RES, so he sees it from the both sides. Then we have Luis Miguel from Universidad de Valladolid, who is presiding over a big project of building a new integrated assessment model, William, the one that can calculate also the limits to growth, limits to the resources. And then finally, last but not the least, Kivan Riahi. He is from IASA. He is one of the leading people in IPCC and integrated assessment modeling. We heard his invited talk today, and I hope discussion today, which will be about how to better integrate variable renewables, which are very difficult beast, into integrated assessment models, which are very important for our climate change talks, for our climate change mitigation. In the beginning, I will give a very short overview of what I see as a problem partially hidden in thousands of pages of assessment reports. Let me first show one table. This is from the assessment report 1. It's about methane. I think everything is correct here, and we didn't do anything since 1990. We could have reduced methane fugitive emissions significantly, but we didn't do that. So the report actually was very good, but it didn't really instigate action in a proper way. It didn't quantify, but it qualitatively said which technologies should be used for mitigation, short-term, long-term. So assessment report 2 didn't give much new information, but 3 was already quantifying new technologies. And you can see here wind, which is considered to be relatively significant technology, and solar, which is considered to be nearly negligible technology. That was 2001. And then we have assessment report 4 in 2007. This is the first one where integrated assessment models actually appear, if I'm not wrong, and I'm sure 2 members of panel will correct me if I am. And then we see here that, well, renewables are significant, but they see much more of carbon capture storage than we see in energy system analysis. In energy system analysis, we see very little bit of need for carbon capture and storage, mainly for, I don't know, cement industry, if we don't invent some new kind of cement. And then if we look here, again, we see quite a lot of carbon capture and storage, nuclear technology, which are not really happening, but renewables are happening very quickly. So my hunch is that there might be a problem in the way integrated assessment models treat variable renewables. And what we learned from locomotion project is that it's not very easy to couple something that has hourly variability and it's fundamentally variable with models that are calculating it on a yearly step. And then in the newest one, Assessment Report 6, with Kivan already has shown in his lecture, we see that renewables are actually the most important solution. So it's improving. We are getting a better picture, but we still think we have another step to do in Assessment Report 7 to get even closer to what we see as mostly 100% renewable future. With this, I would like to invite my first panelist, Shir Kilkish, to give us her initial pitch. Please, Shir.
As opening remarks, advances in renewable energy technologies are providing the important opportunities for society to really act upon. And in this panel contribution, I would like to focus on the emerging advances and possible opportunities for the 7 assessment cycle. The decisions that we make today are determining our climate future. And since the launch of the 6th assessment report, AR6, climate change is continuing to intensify and reached 1.26 degrees Celsius in 2022. And we are increasingly transgressing the Earth system boundaries, including climate change, biogeochemical flows, and freshwater change. At the same time, we increasingly do have the options to change, and scenarios are our essential guides to provide insight in how we can shift from unsustainable energy, land, and resource use. I will have one main point on the need for increasing the representation of variable renewable energy sources, flexibility options, and sector couplings, and 2 additional points on resource efficiency and mitigation adaptation linkages. The interactions between society, economy, and environment are complex, and integrated assessment models provide simplified representations of complex systems with a focus on capturing these interactions. At the same time, bottom-up models can provide advantages in modeling energy systems with high penetration of variable renewable energy sources, and this is especially important to represent sector coupling and demand response for system integration. It's also possible to couple the top-down models with bottom-up models and hybrid models, and this can benefit from the advantages of both approaches through either soft linking or hard linking approaches. In AR6, the illustrative mitigation pathway for renewable energy came to a 66% share of non-biomass renewable energy and final energy in 2050, and also considering the fast cost decreases in wind, solar, and battery technology. On the side of bottom-up models, these can vary in resolution, including in time, space, techno-economic detail, and sector coupling resolution. And there's a myriad of these models, including those with high resolution of sector coupling. And continuing modeling advances, these are supporting the cross-sector integration as a way of increasing system efficiencies. Some of the recent advances include optimization approach to inform energy systems by reaching targeted shares of renewable energy up to 100%, soft linking energy plan with a Python code to determine ways of increasing flexibility options in the energy system, a new version of the H2RES model for the long-term planning of energy systems with high share of variable renewable energy, and also supporting cases for the energy transition. And what we can call perhaps a hybrid model is a novel approach for translating dynamics of the energy model with hourly resolution into integrated assessment models with yearly resolution based on the capacity factors and other emerging approaches. Coming to my second point on resource efficiency, the representation of such emerging aspects as circular economy, material efficiency, this can also increase. And here we see the representation of existing such variables, including material recycling, in the existing scenarios. So this is an opportunity for next assessment cycle. An evaluation of such aspects as reducing the material demand and urban form, which also relates to resource efficiency, lowering energy demand through urban planning, and also supporting and allowing the urban infrastructure to support flexibility. Sometimes these are not represented, and when they are represented, they can either be endogenous, exogenous, implicitly, or explicitly. In addition to this evaluation on the side of global and national models, also there are emerging advances for urban emission scenarios, including not only the mitigation of the emissions, but also possible improvements in land use efficiency for specific urban areas and how these can be represented in the scenarios. And more, we're seeing that integrated approaches are important with multiple transitions on the side of renewable energy, lowering demand, and even additional capital formation that can provide additional value added for society. Coming to my third point on mitigation adaptation linkages, here we see that mitigation policy is influencing the emissions that change the climate, future climate and impacts. On the right-hand side, we also see the dashed line. And in this integrated assessment framework, this is because the influence from impacts and risks to socioeconomic changes is not yet considered in the scenarios assessed. So this is an opportunity. It's also increasingly important to represent more the nexus analyses, including for the energy, water, land nexus, and sustainability criteria is also gaining importance. There are different proposals, but at the same time, it's important to acknowledge the limits adaptation and tipping points that can have feedbacks across human and natural systems. And more we can represent the co-benefits of mitigation options, this can also support us in closing the implementation gap and accelerating climate mitigation. The Agenda 2030, this is nearby, so the target space leading to 2050, this is also relevant, and it can also support sustainable development pathways. So coming to the needs and now to the possible opportunities for AR7, I would like to conclude that first, within the evolving modeling capabilities of integrated assessment models, soft linking approaches are emerging to provide promising contributions. Second, urban form is a key aspect that can support renewable energy penetration, demand flexibility, and resource efficiency. And third, pathways that inform ambitious climate action with co-achievement for sustainable development goals and beyond are gaining importance. Let me conclude that scenarios are our essential guides in this critical decade of action and beyond for our climate future. And our climate future depends on this critical decade of action. Thank you, and hvala.
Thank you, Shirin. Henrik, your time for initial pitch.
Thank you very much. A lot of things can be said about this important topic here. I have been allowed 5 minutes, so I have made priorities. And the first thing I would like to say is that if a model is good or bad, if a model is something you can use or you cannot use, or you can benefit from using or not, boils down to it depends on what wish to investigate what your study is. So I think that will always be very important to ask yourself before you even ask yourself about which model should I do. And for my part, what is normally, in general, my purpose and what I would like to do, and also why I then use models and tools and software and all these sort of things, is that I wish to investigate how we can implement and do the green transition. And I wish to do how we can do that in a doable, technical, liable, economical way, and so on and so forth. So this is my purpose. Now, given that purpose, I would like to communicate 3 things here on the 5 minutes I have. The one thing is that the political talk of the year, so to speak, have changed from 20 years ago or more when I started this and what it is now. And right now, as I hear it, it is becoming climate neutral. It is society should become climate neutral or even climate negative. But the point here is it is climate. That means that when I, as an energy analyst, is trying to find out how can we do the green transition within the energy system, I cannot only look at the energy system, I have to also look a little bit with at least one half eye on the agricultural and the industrial processes and the rest of what is part of greenhouse emitting parts of society. Otherwise, I cannot really find the doable best solution for the energy system. So that's the one point I would like to make. So when I'm looking for tools, it could be tools that concentrate on integration of renewable energy, as we talk about today, but at the same time, they also have to have at least a possibility of having one eye on the other sectors. That was one point. Another point I would like to communicate here is that out of the experience when I have been doing this for many years and doing it over and over and over and again, then there's something that it repeats itself and come more and more clear to you. And one of the things that is really clear to me, and I echo what we have just heard, is that you need to take a cross-sectoral approach. Otherwise, you will not be able to identify the best and most doable solutions. This is what we have tried to communicate in the concept of smart energy systems. We cannot look at the electricity sector on its own, the heating and so on and so forth. We have to look upon it in a coherency. It's only when we can take this cross-sectoral approach we will be able of identifying the best solutions. So that's why when I develop tools, also when I use and apply tools, I really look into if those tools can be holistic and include as many sectors as possible and look into the future and can include in the analysis all those cross-sector technologies linking the different sectors. That is essential. And then the last point I will try to make, that is always seems to be the most difficult point for me to make, and very often I tried it before, I feel a little misunderstood, but I will try again today. And that is because I'm an engineer, and although there are many engineers here, engineers, we always like to optimize things. We take a machine and we'll have the optimal operation or the optimal design or whatever it might be. We like to identify the optimal solution. But with my topic, that is to look 20, 30 years into the future and then designing something for a whole country or Europe or the whole world, then an optimal solution for society 20 years from now, is that a concept that makes any sense? And to me, it doesn't. And the problem with, so I advocate against optimal solutions and optimization tools I argue for simulation tools that identify various options, and then you can better see the whole landscape. And the reason I argue for that is not because I have anything against identifying optimal solution, but I can see if you put everything into a computer and ask it to identify the optimal solution, and I've seen this many times, then you blind yourself. You are not getting wiser. You narrow yourself down and can only see the one and only way. I cannot really see all the other ways. Just one example. Some years ago, one of the many climate commissions we have had in Denmark were trying to identify the good solution for the future, and they used an optimization tool. And this optimization tool came to the result that we should have no PV in Denmark, no photovoltaic in Denmark, because at that time photovoltaic was very expensive. Now it's very cheap, but at that time it was very expensive. So if you put all the numbers into the model, it come out with the result no photovoltaic in Denmark. Are you wiser out of that result? I don't think so. So it's much better to see if we have certain number of photovoltaic, if we don't, what will the different outcome be? And in my experience, we will very often come to the result that there will be a lot of optimal, near optimal solutions that you cannot really argue that the one is more optimal than the other. But you blind yourself if you only look for one solution. You should look for several solutions at the same time. So it is only 3 points, so I don't need to repeat them in the takeaways here, but so I think you can record them. Thank you very much. That is all from me.
Thank you, Henrik. Felipe? Your 5-minute speech.
All right, thank you. Thank you, Neven. My name is Felipe Feijó. Basically, I want to try to describe a little bit the GCAM model, the Global Change Assessment Model, and how we have used this model in the Latin American context, but more specifically in Chile, and basically how we try to use it to inform some policies to the Chilean Ministry of Energy. So first of all, I wanted to introduce a little bit about the background of the model. GCAM is the Global Change, now it's analysis model. It used to be assessment model, so they changed the name recently. And as Shir was saying before, EAMS, and specifically GCAM, is a global model. And when we mention model, it's basically because we try to model somehow the whole world, but not only from the energy system point of view, but also from different interconnected systems, such as land. So we actually model 384 different land regions in the world. From the water point of view, we do model 235 water basins globally. And all these interconnections are basically linked with the energy system and economic system, for which basically GCAM considers 32 global regions. So all of these regions from different systems are endogenously interconnected, and when the model is being solved, all of this is basically being taken part, not in the optimization as Henry said, because GCAM is a partial equilibrium model. So there is some optimization here, but it's actually an equilibrium model. If we go a little bit deeper into the structure of the model, we basically can see a lot of different dynamics being represented. And because we are mostly energy system modelers, I wanted to focus a little bit more on the energy system. And we can see that GCAM actually considers a lot of the dynamics that we normally do consider when we model energy systems. So electricity generation, hydrogen, final energy use, but something that is actually interesting is that within GCAM we're actually modeling primary energy production. So basically coal production, oil, basically coming from different resource corps or supply corps for the globe, for the 32 global regions that we do consider in GCAM. We can also model in a high detail the demand sectors. For instance, I'm showing here how we model the industry. In the latest version of GCAM, GCAM 6, now we actually go a lot further in terms of representation of industry. And in the Chilean context, mining is particularly important. Chile is a probably one of the biggest producers of copper in the world, and hopefully lithium in the short term. And now we can actually model in high detail mobile and non-mobile energy use within the mining sector in Chile. We also model water use, also very critical and important for Chile, agricultural demand and non-agricultural demand, and power sector, domestic, municipal water use, and so on. Hydrogen is also very important for the Latin American context in particular. So we can model hydrogen production from different sources, particularly electricity and renewable electricity, and also the transportation sector, very important for decarbonization pathways in Chile. We actually implemented an electromobility strategy a few years ago. We can actually model and assess with this model. What we've done, the original version of GCAM actually considers, as I mentioned before, 32 global regions, but we did an effort to actually further disaggregate GCAM for the Latin American context, and we now basically have a version of the model that considers a country-level disaggregation for Latin America, and this basically allows us to do a lot of different analyses that are highly relevant, and I want to basically show a couple of them now. First of all, we did this study a few years ago with colleagues from the Pacific Northwest National Lab. Basically, we look into the stranded assets implication of the Paris Agreement in the Latin American context. We do find that basically we can meet the targets, but with a very high economical cost, okay? So that's something that we really need to take into account. In the Chilean context, we did some basically analysis to see if we can reach the Chilean indices. We also find that this is possible, but there is, basically there are some sectors that are hard to abate, for instance, the transportation sector. And this is something that is very interesting, and why we think that EAMS, and in this case GCAM, is actually interesting, is basically when we want to look into the relation between the energy sector and the land use. What we can see in this plot right here, this green area, is basically what Chile relies, how much Chile relies on forestry and land use, basically sequestration, to meet, or basically to reach carbon neutrality. So 50% of the emissions are actually being sequestrated. This is slightly complicated in the Latin American context because we have, at least in Chile, every summer, a lot of wildfires, and it's very, very critical. We also have a lot of dry years. So basically relying on forest capture to meet the NDC is very, very risky. And therefore, we need to model the interaction between the energy sector and the land use. Because if Chile basically relies on this, we need to be able to have a tool that can actually model the synergies between these two sectors. And that's something we can actually do with GCAM, and we basically have done this, and we basically define some likelihood scenarios in terms of how much we rely on forestry sequestration. Finally, we did some studies with some US laboratories. The Pacific Northwest National Lab is one of them, in this net zero in global initiative. We did some NDCs and climate neutrality targets, and not only for Chile, but also for Argentina. And this, basically, this report is publicly available, so I highly encourage you to download it and take a look into it. We did analysis for Chile, Argentina, Indonesia, Thailand, and Ukraine as well. So that's it. Looking forward to the panel. Thank you, Neven.
Thank you. So I would like to ask Luis now to give initial pitch. 5 minutes, hopefully. Okay, 1 minute more than 5, it's okay. Yeah.
Hi. First of all, I would like to thank Professor Neven and also SDEWES team for the organization of this panel, and of course for the rest of the conference. Well, I'm going to talk a little bit about the work we have been done in the framework of locomotion related with the integration of renewable variability in the integrated assessment model that we have developed, that is called William. Well, even when most of you know quite well what is integrated assessment model, let me keep some key ideas about that. An integrated assessment model is a computational model able to represent in the same framework variables of different, let's say, dimensionalities. So it represents variables from economy, from technology, from environmental, from social, from materials, whatever. So the key issue is that these kind of variables are quite related. So there are a lot of feedbacks between them and relationships. So we can have an overview of what is happening in the global system. So therefore, usually we use a geographical scale that should be at least national or maybe European, regional, or global, as it has been said already by my previous colleagues. So one point that is relevant to mention here is that usually the time scale for this kind of integrated assessment model is annual. We use annual data mainly. And that means that, for example, for energy demand or supply demand, we have the total energy demand, the total annual demand in 1 year. So this is a little bit different to these kind of technical issues that you have been talking in most of the papers in the conference. So, however, what is the problem? The problem is that energy variability, mainly due to the renewable energy sources, has a different dynamics. The dynamics of this variability is mainly hourly, even less. So the problem is how to capture this dynamic variability in a model, a simulation model that is mainly yearly time scale. So when we don't take into account this kind of variability, the problems that may arise are related with, for example, curtailment, variation of the capacity factor we have considered, and of course, other problems like power to X, flexibility options, and so on. So we need to include in this kind of integrated assessment models some variables to take into account this new problem. Furthermore, these kind of problems like curtailment and so on is increasing due to the energy transition, renewable energy is going to take a more and more importance. So we need to take into account into this kind of integrated assessment models. So this is just some data to show how curtailment may be in European countries. These are some historical data about the curtailment in the historical framework of the last 10 years, more or less. So it's a relevant problem even with the historical data, but in the future, it should be higher, probably. So what are the approaches that are now using in order to solve this kind of problem in the integrated assessment model? Let me explain that there have been some, let's say, historical approaches based mainly on historical energy generation and consumption data. So people use historical data in order to tune some functions in the integrated assessment model. So in order to take into account this kind of, let's say, variability, curtailment, capacity factor, and so on, some functions has been developed in these models, but basically learning from historical curves, historical data, from daily behavior, or whatever. Usually they use statistical data, patterns, and so on. The new approaches are based mainly in the use of what we call energy planning software. The energy planning software are more detailed models that are able to represent technologies with a more detailed components, and usually they use a hourly time scale. That means that may be able to represent quite well the variability of the renewable energies. So what is the trick? The trick is just to use the energy planning software, the energy planning models, in order to have a best estimation, the best possible estimation of variables like curtailment, capacity factor, and so on. So the integrated assessment model provides the energy planning model with, let's say, something like scenario parameters, capacity that we have in all the years, something like that. So the energy planning software is able to obtain a more precise data about what is going to be the curtailment, the energy consumption, and so on. And this information is given back to the integrated assessment model. It can be done in different ways, of course, both methodologies in different ways. In this sense, at least, there will be possible to develop, let's say, something like a soft link way. So you can do it offshore or offline, the estimations, and it may be also done online, with a hard link. So, going back to the William model, the integrated assessment model William is the one that we have developed in the locomotion project. In our case, there are around about 8 modules, 8 modules related with economy, environmental, including land use, materials, society, and so on. Obviously, these models are interconnected. So what is happening in economy have influence on energy. What happens in energy have influence on materials, materials on environment. Everything is related with society indicators, and feedback, again, on consumption, economy, and so on. So I'm not going to get deeper in all the relations. Obviously, I'm going to focus only in the energy model. In the case of energy model, that, by the way, has been explained in another session in this conference, mainly we have an input that comes from the economy model, that is the demand of energy in economic units. This economic units is transformed in energy units through the energy intensities, and we obtain the final demand. This final demand go into the transformation model. In transformation model, we need to allocate the different alternatives to produce this energy according to the energy capacity, all the energy infrastructures, and so on. Also, the limited resource from renewable resource, but also from fossil fuels resource, of course. And, of course, we need to use a specific model just to take into account what is the variability of these renewable energies. In order to take into account this renewable energies variability, the method we use is something offline. So offline we design a huge quantity of experiments with all the alternatives for, let's say, a country. Alternatives, I mean, related with the capacity of production, the capacity of storage, wind, solar, any kind, hydro, any kind of possibility. With these experiments, we run in energy plan. In this case, we use energy plan for energy planning. So we obtain the outputs. Outputs, for us, the most relevant outputs are the curtailment and the capacity factor. And we try to obtain a regression function that we are going to use in the integrated assessment model. So finally, we use a regression function that is able to represent more or less what is happening with all the alternatives. And in this case, this is one of the results. In the X, you can see the prediction of the model. And here are the real output from the energy planning, energy plan software. So in theory, the red line, just in the middle, should be the perfect fitting of all the data. Obviously, the real cases are the blue dots in the graph, and some of the cases are more or less far from the perfect fitting in the red line. But we consider that this approach may be sufficient to represent, in this case, I think is the capacity factor for wind energy. So the more detailed way is in a paper that I'm going to explain here. And just to end, just some comments. Obviously, this problem of variability in energy, mainly for renewable energies, is quite important, and it's a big challenge for integrated assessment model. The way to do it is maybe vary. There are indeed several alternatives. I have shown some of them more or less. In the case of William, we have tried something that we can call soft linking between energy plan and our integrated assessment model, William. The results are maybe enough good, but I think we can improve it if we got hard linking. Hard linking means that we can online call to energy plan and obtain every year the new results to continue with the integrated assessment model. And that's all. Thank you.
Thank you, Luis. Now I would like to invite Kiwan. The floor is yours. Initial pitch.
Thank you.
Yeah, thank you. I can actually just perhaps connect to what my colleagues have already said. You saw that basically there are very different types of models. We have heard about optimization models and simulation models, very detailed systems engineering model like William compared to the GCAM model, which is a simulation model but with a bright scope, wider than the energy scope. And I think the really important issue to keep in mind here is that we use these different models and different designs in order to answer also different questions. So there are horses for courses, and there are also models for the right question, and sometimes one can use a model also for the wrong question. So it's always important to have this match in mind. Basically, integrated assessment models are, I think, this type of models, as we have just heard it also earlier, which try to, at the one hand, represent the whole world in a very holistic way with all the different sectors embedded in the economy. So how you basically make decisions in the energy sector, what does it mean for the overall economy, but then finding the sweet spot by adding as much technological and sectorial detail as possible. So you try to find common ground there when doing when doing integrated assessment models, and that's why in many areas they are actually not representing the system with all its detail, but there are other more detailed sectorial models that we use to couple our tools with, or that we use to parameterize certain development. And the same is, for example, for renewable integration that I want to talk now a little bit. So I will talk about the global IASA integrated assessment framework message, the energy part of it, and focus primarily on the systems integration of variable renewables. So if you want in a system appropriately integrate variable renewables, there are a few minimum characteristics that you need to keep in mind and that you need to teach the model. One is system flexibility generally decreases with increasing variable renewable share. And if you add variable renewables, you need to make sure that you have technologies within the system who can basically chip in when it's dark or chip in when there is no wind. So this flexibility needs to be there. Another important aspect is the capacity adequacy, difficult word. So not every technology can satisfy every type of load. Yeah, so if you think about a complex load curve, there is a base load which the energy system basically the consumers want to have all the time, but there is also the nasty peak load where a lot of capacity is required. And one needs to satisfy that peak load at any point in time. And you need to teach that the model that not every technology actually can do that. You cannot rely on solar to satisfy your peak load directly. You need to go over a detour of, let's say, producing hydrogen and then having a little bit storage in the system so that you can still satisfy this peak load. And you need to tell your model, okay, there are base loads and there are peak loads. You can, if you are clever, you can make your solar technologies dispatchable even if they are multi-purpose. But all of that we try to include into our modeling frameworks. Then we need to understand the grid dimension. So if you include more and more variable renewables, what does it mean for the grid? So are you going for many island solutions, or are you going for a really integrated grid? Because in a renewable system, you need actually more grid rather than less grid, so that you can basically connect different distributed sources which can compensate each other, so the grid costs increase as well, and you need to integrate that into your tool too. And then finally, there will be situations where you have curtailment. Basically, in order to find a good system design, and now I don't want to use the word optimal, but actually you might want to know the optimal system design as well. So you want to find a good system design where you minimize curtailment. Yeah, so curtailing energy is wasting energy. So you don't want to do that. But if you get then to really high solar and PV, solar and wind shares, it's becoming more and more difficult to avoid curtailment, and you need to make decisions there. Either you curtail a little bit, you store, or you do other things that they want to bring. So how do we integrate this into a very aggregated, global, integrated assessment model that covers all the different sectors? Generally, what we do is we collaborate with colleagues who do very detailed power sector modeling. So as we have heard it from the William model. So I don't have to go into too much into that direction. So what we have done here basically is that we had the detailed power system model. PIPESA for Europe. We ran that model with very different combinations for wind and solar, with different assumptions about how much electricity transmission expansion you can have, how much storage will be available to the system. Is it short or long duration storage deployment that is available? What is hydrogen available? The heating demand, because these are connected problems, etc. And then we ran basically this very detailed, spatially explicit European power planning model, power plant and grid model, and looked at different, for example, curtailment rate of solar with different solar generation as the percentage of the total energy demand, and got, of course, different curves depending on the combination with wind. And this is the case where we assume there's actually no storage available. So quite a lot of curtailment if there is no storage available. And then looked at our aggregated integrated assessment model, which basically tries to have a parametric representation of these combinations together, so that we don't have to optimize or don't have to simulate all the combinations. And that's the way that you can bring basically disciplinary, sectorial expertise and information into more aggregated integrated assessment models. And that's generally how we have done it. Another key field, and I think that's discussed too little, is the absolute critical need of energy storage. So I mentioned that also in my lecture, so sorry for showing a few slides which are the same as I showed actually yesterday. But I think it's really important that we emphasize more on basic research on which of those technologies might actually work at scale. We know that pumped hydro will work at scale. We know that batteries for short-term storage are working and becoming more and more economic, but there are many, many other options as well. And if we include them in our tools, actually the solutions change quite a lot depending on which storage options we use. And I have explained them yesterday in my speech, so I don't want to go into more details, but the important thing is that depending on the circumstances that you live in, there are very different storage potentials always available. You don't need to live in the Alps to have mountains. Then you have a lot of hydropower, pumped hydro. If you're in the coastal area, there is an option. If you are in other circumstances, there are options as well. And what we tried is to basically look for different world regions into the energy storage capacity across different regions. This is now for mountain gravity. Particularly in areas with high water scarcity. You can also elevate other types of weight to store energy, and you can see that the potentials across different regions are potential differences are quite large. And then we looked also into potentials of marine energy storage, which are very large, but also very unevenly distributed. You need quite deep coasts. So in Europe, we have relatively low potentials, but you have on some of the coasts quite large potentials here to basically store energy also economically. If you do an economic assessment of these different options, you can see that energy storage costs of these different options can vary quite a lot. We started to implement them in our tools. So we have now mountain gravity energy storage, electric truck storage, lift storage, seasonal pumped hydro storage included. What we're working on at the moment are these very big storage options where we work with engineering teams together to understand the construction issues and also to understand the potential costs and also the potential learning into the future. 20 years ago, you mentioned it, solar costs were extremely high. Nowadays, nobody's arguing about costs anymore. At that time, when we showed high solar penetrations, everybody was showing at us and saying, but they are so expensive. And nowadays, everybody says, why didn't you tell us more solar at that time? 10 years ago, simply nobody thought it would be that rapid, the cost decline. Thank you.
Thank you. I would like to invite now my panelists back to the panel. Sorry? 5 more minutes. Yeah. It always goes like that. Okay. Well, the cheapest system would be solar only with interconnected continents, by far, because there is sun shining somewhere all the time. It's geopolitically not possible, and we are not going to see it anytime soon. But this size of granularity of your system is important when you think about grid versus storage. So if we consider that continental grids will be essential for climate change mitigation, then we actually see quite a lot of capacity in variable renewables, especially wind, that could be trusted on European level. For example, on last 5 years, wind was blowing at some 5 to 10% of the nameplate capacity all the time. So there was no Dunkelflaute, actually. It may happen, but it is different than it will look on a country level, where obviously there is times when wind is just not blowing. This is one point that I think it's very important to think of. So when we think about energy planning, we usually look from national point of view, but is this paradigm going to stick in the mitigation times? Okay, maybe in Africa, but what about Europe? Europe is the most difficult case because we have very dense consumption and not enough renewable resources. That's one point. Another point is heating and transport are significant part of final load. So if we electrify those, and if we consider those loads being shiftable in time, we actually get a huge new demands which are dwarfing the legacy electricity demand, which makes economics for overbuilding wind and solar. And then if you add hydrogen there, you get even more of such a demand. And then this is what we see from the point of energy system analysis. If you look at the optimized system, okay, not a good word. I actually agree with Henrik, but you know, you have to understand what you're doing. If you're doing simulation of optimization, anything, you still have to understand. So, okay, if we look at how cheapest we can get with putting things together, which might not be politically possible, so we should put some limits to socio-political boundaries of the system. We see that we actually don't have such a huge problem in running system on renewables. So maybe I would like first Kivan and then Henrik to give their view on this discrepancy that we see in different models on solution of this equation. Who wants to start?
I just spoke, perhaps Henrik wants to.
Okay, Henrik.
Oh, that was a long and complicated question. Don't expect me to do a short answer on that, but let me give it a try. I mean, of course we will get different answers on different questions using different models. I think that's good, because then we get wiser. Then we get wiser both on which questions should we ask, how should we formulate them, and what will that mean for the answers we get, and everything. So, but if I just connect to what I can say is, where am I in answering what is my purpose, namely to identify suitable ways to the green transition. And where I am is that I think there are some fundamentals when we do this. And when you start, Neven, by mentioning that the solar is shining somewhere, always, and if we only, yes, but the interconnectors will be extremely expensive. So this will be a crazy thing to do, I'm sure. But some of the fundamentals that I have sort of grabbed my hands on when trying to find the best solution is that the cost of storing energy, and now you mentioned the different storages there, I always group them into 4. And those 4 is, what type of energy do we wish to store? And I always say, if we wish to store electricity, that could be many things. You mentioned some of the storages, pumped hydro, batteries, and so on and so forth. Electricity in, electricity out. Then the cost of doing that is in the order of magnitude 100 times more expensive than storing heat or thermal energy, heating, cooling. Heat in, heat out, or heat out, heat in if it's cool. And that again is 10 times more expensive than storing gas, methane or whatever, green methane, and that is again 10 times more expensive than storing liquid fuels, like methanol or whatever we could use in the future. And that's why, in my view, the smart energy systems context and approach is so incredibly important. Because if you disregard it and only look at the electricity sector, then you corner yourself up into very high and expensive investments in grid, that is very expensive, and the most expensive storage technologies of them all. But if you generate a context, no matter if that is in Denmark or in Australia or anywhere, where you have more than one sector, cooling, heating, electricity, transport, not at least, then you realize that you'll have to do some power to heat, power to gas, power to liquid fuel, power to transport, we can call it many things, power to X, as it's called now. And you have to do that not for the sake of integrating renewable energy, but for the sake of decarbonizing the transports and the heating and those sectors. And then you get for free a much affordable solution in terms of storage. And I will say we should seek that potential always before we seek the potentials of connecting countries. Sometimes when we say that Europe is disconnected and don't have transmission lines enough and we have bottlenecks between the countries as in many other parts of the world, I see this is a wrong way of looking at it, because what you are doing when we in Denmark build a transmission line to England, that is basically connecting an electricity system in Denmark that is disconnected from the heating and the transport sectors. and connected it to an electricity sector in England that is also disconnected from the heating and the transport and all the other sectors. And this is like two blind people trying to help one another, and they cannot really do it. What we should do first is take the disconnected electricity sector in Denmark and connect it to the heating sector and the transport sector, which is much better to assist the integration of renewable energy. Sorry, it was a long answer. I'm not sure I even answered your question, but at least I gave it a try.
Yeah, I agree to a lot that you, that you said, Henrik. I was a bit surprised about the emphasis on the costs, though, because you said before you don't want to optimize costs, but costs are of course important in the system. Perhaps one thing which so we actually tried to emulate exactly your question. Should we? How much how much intercontinental electricity connections could the system need during the transformation? So it was a paper in Nature Energy 2 years ago. Our main collaborator was the Global Interconnection Company. This is it's a Chinese company, the fifth biggest company of China after the digital company. So they had marvelous data about possible connection ways between different renewable sources. They are very, very strong in that. They actually, their main interest was they are now championing the ultra high voltage connection lines with very, very low losses, and they were interested in, so they built just 3,000 miles of interconnection lines to connecting north to the south. It is a gigantic investment. And they were basically subsidizing the neighbors. So if the neighbors were interested in connecting to China, they said, we pay 50% of that, just let us connect the grid. Many were very suspicious because they were all worried that China is actually interested to get its coal electricity transported further to the west. So it never really took off outside China. But in our modeling, actually, it's exactly what you said, what came out. We had 10% was the intercontinental, in a very optimistic case, with very cheap connection lines. We had roughly 10%, and because of exactly what Henry said, because the alternatives in terms of going to extra power, hydrogen, and investing more into the local solution, and at the moment when you connect the electricity grid to the other sectors, wasn't making it so attractive. So I think there is a potential for these interconnection lines, but one should not overestimate them. At the moment that you go and look exactly at the costs, you can see that other options are at least given the current cost structure favorable, in my opinion.
Anybody wants to comment? Or
Maybe.
maybe? Okay.
Well, but you asked about the possibility of interconnection between continents. I think we will be able to improve and to increase a lot the connection in each continent. Let's say in Europe, we can improve and extend, but the intercontinental connection, I think, is quite far from our models just now, at least for the model, and I think also from reality. Not only, but probably mainly for the socio-political reasons you mentioned, but also maybe for the technical reasons. We cannot grow forever in this kind of energy consumption, and also we have to take into account not only the economic prices, the cost in terms of economic units, but also the cost in terms of materials, and materials are finite, so we have no materials for everything we want to do. So. Furthermore, I would like to tell that sometimes in this kind of forum that we discuss about technological issues, so obviously most of us probably are engineers, and we think about different techniques and also different optimization and so on. But sometimes we forgot about the social variables. What can we do, for example, with social behavioral change? For example,
or the social barriers. Most of our technologies, people said, no, I don't want that. So sometimes I think we need to be nearer to the, let's say, social problem, society, and what they think about the real problem. What are the price they would like to pay? The price in general terms, I mean. What kind of social behavior they will be able to do, what economic price will be able to do. So it's not so easy to develop a technological vision of the world and say, that's okay. This is just my point. Thank you.
Well, that's a fourth dimension to the third one that Kievan mentioned, yes. Well, my intercontinentals were just provocation in a way. I don't think we should look into that as a serious option. Felipe, you have, I think, or your PhD student is trying to compare GCAM results with H2S results, and you are getting much more renewables when you do it with energy system analysis model than with EM. Can you comment on that?
Yeah. Can you hear me? Yeah? Okay. So, I mean, a background basically of why we are trying to do that. On one side, and I know where your question is going, in GCAM we don't consider variability of renewable energy, and that's why we want to do that. And the main objective is actually try to quantify whether or not the results that are coming from GCAM can be, if they are basically feasible from the operational point of view in a power system. So it's more or less doing a downscaling from the results coming from an EM into an operational model, which is basically like what K1 was saying with pipes, what they do, try to quantify or try to do this, soft linking between the models. And what we actually find is that you can actually integrate the results coming from GCAM in terms of capacity investment for different technologies, but you have huge curtailment or excess of electricity, and we quantify that to be around 10 to 15%. So GCAM is actually producing less electricity that is needed than the electricity coming from H2S. So we basically need more, this is basically coming because GCAM doesn't consider storage, GCAM doesn't consider variability of renewable energy. So when you put those constraints into place, then you end up basically needing more electricity than what GCAM actually provides. We need to work into that to actually see how we can improve the EM point of view, the EM's modeling side. And that's what Luis Miguel probably is trying to do, and I think that's important. But that doesn't mean that GCAM results basically are not valid. They try to quantify other dynamics, try to put into place other policies or other dynamics that we cannot model with the energy system. So we need to try to balance the tools that we need to use to answer basically different questions.
Thank you. Going now into opposite extreme, from the world to the local community. I actually fully agree with what Henrik said, that we can solve quite a lot of problem using integration of local systems. So I have a question for Shir. How to use cities as integrative vectors for integrating power, heating, cooling, transport, industry, fuels, everything together.
Cities are where the integration is and can take place in the future. So it's where the buildings are, buildings can be flexibilized, it's where the transport is, both public buildings, metros, and electric buses, and these can be flexibilized. And the heating, so if you have district heating, the heat pumps can work in times when there's excess wind or solar, and support either can be supported as thermal energy storage, but the cities are the dynamic places, so the resolution that can be captured in cities are relatively higher with all of this granular detail. When we come to how this fits in, when we're trying to increase the renewable energy share, we also need to think about how we can diversify the flexibility options, because when we diversify and not rely on grid-scale battery energy storage, then we can find relatively perhaps less costly and more cost-efficient options that exist and can be transformed in the existing infrastructure that we already have in the urban area, the cities, the buildings, the transport, even waterworks. So the waterworks and the electric equipment can be part of demand response. When we look at how Europe is expecting, so one study from Joint Research Center looked into, in 2050, it projected the flexibilized energy demand by projection about 33% of total final energy. This is daily, weekly, and even monthly, they considered that. But it depends on how you model it and how you make the projections and what kind of flexibility options you're considering and whether they're including more diverse set of flexibility options that go into that area. So the research work in this SDEWES community also looked into supporting systems with 100% renewable energy sources, how the electric demand can be flexibilized up to 50%. So it depends on what was considered, how you model it, how you, that's the modeling capabilities that is providing the insight into this. So the more we diversify, and coming back to cities, your original question, there are a lot of opportunities that can provide perhaps lower cost, more feasible options, and the integrative aspect of cities.
One more sub-question to you. As a part of assessment report 6, you worked on that area. How difficult was it to push the city agenda into the report?
We had urban systems as part of the given outlined to us, and that was agreed previously. When we took the task, we had a discussion of how we should approach it. Urban systems is very complex. Energy is there, transport is there. We should think of urban systems as cross-sectoral. That was challenging because relatively you find a lot more scientific literature that looks specifically into buildings, specifically into transport, and the cross-sectoral aspect is very important, but relatively the presence in the scientific literature can be relatively less. But we did address this gaining importance as emerging scientific literature, that cross-sectoral aspects are very important. And now, not only looking back into what we did in AR6, which we do have a very good chapter on urban systems, but looking forward to the 7 assessment cycle, we will have a special report on cities. Climate change and cities will be the first product to be delivered in the 7 assessment cycle. And right now, so if we did that assessment, the literature is constantly growing, it's accelerating, and I think the scientific opportunities, modeling capabilities that we have and are continuing to have, we have much more scientific evidence now to support the cross-sectoral integrative aspects that can go into the cities and urban systems.
Thank you. So we have cities which will in future be a place where most of people will live. They will be concentrated demand for energy, not necessarily source. And this actually looks difficult to model with models that are on national level or continental level or global level. But on the other hand, if we look at it from the other side, we have concentrated parameters in cities, which is actually very beneficial for our national models, because there we work with concentrated parameters. So I think this is actually quite, it will work together to model wider regions, considering that most of people will live in cities where we can exchange between different sectors. I don't know if you would like to comment on this city versus national level conundrum in the modeling. Maybe, yeah?
Yeah, maybe from my experience on the advisory board of Vienna and the Austrian situation, I can say that the advantages in the city, the big density that we have, which makes cities extremely efficient, can also be and that density can also in the near term also be a challenge. Yeah. So if you think about if you want to have heat pumps and complete electrification of cities in terms of transport, you need quite high capacities. And in a city, to change the electricity grid is not easy. So that's what the city of Vienna is struggling at the moment. Although everybody knows that it's better to electrify, probably they will go to industrial heat pumps and district heating and even increase the district heating capacity. There's quite a discussion about how to do this, and there's also socially a quite big challenge there, because we all know that electric heat pumps in houses with floor heating is not only cheaper, it's more efficient, but it's also more convenient. But if you have a gas boiler that is working, that is relatively new, we discussed it a little bit yesterday, that is new, how can you set the incentives to basically switch to this new electrified system, when at the same time you have the whole challenge that you need to completely dig up your city to increase also the capacity. So cities have the advantages because of the density, they have also the disadvantages because of that.
I'm sure Henrik will have a strong response to this.
No, I'm not directed to this, but I would just say that around 10, 15 years ago, doing some more principle analysis on the main question here, that is, how much do we need to connect the countries in order to better integrate renewable energy? And already then we could see that, and this is a little bit country specific, so now I say Denmark, but I think you can still learn the principle out of it. If we took Denmark at that point and tried to integrate a lot of wind and PV, what we could see was that if we only looked at the electricity sector, we could replace up till around 20% of our coal-fired power stations and so on with wind and PV without having really curtailment problems or anything like that. Around 20% will run into the wall. If we then broaden out our perspective, not only looking at the electricity sector, but looking at the electricity sector and the heating sector, then we could go to 40%, still increasing the energy efficiency, at least not losing any energy efficiency in the system. Then we run into the wall again. But then if we included the transport sector, and those times electric vehicle was not so likely as there is now, but both direct and indirect via power to X, then we could go almost all the way. And I'm saying this because when we talk about in Europe and other places that we should have a strong electricity grid so that when the wind is blowing in Denmark, we can export it to Spain and they will have solar power and then we can export that back when the sun is shining and so on. I will claim that if you only look at the electricity sector, you'll find feasibility in a certain number of transmission lines. But if you include the heating and the cooling sector, they will not be very feasible. And if you include the transport sector, I don't think they'll be feasible at all. So that's what I'm trying to communicate, the context of decarbonizing the whole energy system. And then you can even look beyond with decarbonizing the whole society. Means a lot to if it turns out to be feasible to do this interconnection. So my point again is, let's do the smart energy system, the integrated energy system, let's integrate first before we start building interconnectors and not so affordable storages.
Power to heat can be done in two ways. Mm-hmm. One way is individually with heat pumps, and the other way is through district heating. Mm-hmm. I was hoping that you would say why district heating is so much better than heat pumps, at least in dense areas. But since you didn't,
I can.
I can do it.
Oh yeah, please.
Because it's so versatile, we can use different types of energies: waste heat from other sources, solar energy, which is stored seasonally, or geothermal energy, or heat pumps, and the storage on a district heating level is much cheaper than on individual level. And furthermore, the space is very expensive in apartments. So having an individual heat storage is possible. We can use it to play on the markets, so to only heat water when it's renewables, but it will take a certain amount of space. If we do it on a district heating level, space is not a problem. And this is the main way how to avoid peak boilers, because if we don't have heat storage, we will need peak boilers, and we don't want to have peak boilers. Did I answer?
Yes, but excellent, Neven. If I can just add a little numbers also to say this, because we made because there's the past and there's the future. And we look into the past, one of the major reasons and sources for district heating was the waste heat out of producing electricity on coal-fired power station. Of course, that should not be there in the future. But we have also looked into the future. And in the case of Denmark, we have industrial waste heat, and if we to that add the waste heat from the many data houses we are building, and if we to that add the new potential of waste heat from power to X, that as Eva illustrated, and if we to that add the potential of deep geothermal in Denmark, then we have calculated that in the future that will be enough to cover the whole district heating of Denmark in a situation in which 70% of the houses in Denmark is connected to district heating. And this is just recycling low temperature heat that we don't really have any other use for. Then, of course, in real life, we cannot make it meet because it has to be at the right place at the right time. But we find it doable to make half of it being recycled. And then we can put solar thermal and heat pumps on top of that. And this just makes a much more energy efficient system. And on top of that, those heat pumps in the district heating, as you mentioned, will be extremely flexible and will then further the integration of PV and wind, at least to a certain degree.
Well, I think that the things become more complicated if we go south, when there is no heating. Then we don't have this opportunity of power to heat. There is some heating in Spain, but not that much as in Denmark. So in Spain we have to think about maybe other solutions. Also Chile. Maybe you would like to comment on that?
Yes. So, actually, in Chile, there is probably one district heating market right now. And if we are lucky, we have one. So there is actually no district heating. We have 2 or 3 pilot projects. One in the city of Temuco, where I'm actually from. It's the most polluted city in Latin America. So basically because of biomass burning, wet biomass, so it's a huge problem. But we don't really have district heating. So what we don't really see it as an option to basically integrate renewables. And what we're looking into it's long-term storage or medium-term storage, and in particular CSP. So we are actually building, or we already built the biggest CSP power plant in the Atacama Desert, started operation a few years ago. And we are looking into pump hydro also as an opportunity in the northern side, in the southern side as well, and stationary storage. So that's basically at least for the Chilean context, the most appropriate solutions instead of district heating or power to heat. Basically, there is not much heating demand in the half of the country, basically, in Chile. We have the driest place in the world to start with, so it's a totally different context.
Well, let me give you a more, let's say, general answer to your question. Of course, in the case of district heating, there are some cases in Spain, not many, but there are some cases. But from a general point of view, I think that the cities are like a micro world experiment in which it's much more easier to have many different options for sharing. So sharing production of energy, consumption of energy, maybe heating, but maybe also transport. You can share transport, you can share housing, you can share appliances, you can share photovoltaic installations. So it's a very good place just for this kind of sharing opportunities that in general terms usually are much more efficient than individual use of any kind of energy consumption or production in general terms. By the way, in the case, coming back to the original question, in the integrated assessment model, usually we have no small cities, the cities, because it's too small for a national model or whatever. However, that we are able to capture the behavioral in the urban households as a difference to the rural household. So in our case, we have 60 different households, so half of them are urban, and the behavior patterns for consumption energy are different to the rural households. So from this point of view, as the population in the urban areas increase and the behavior maintain the tendency to be more efficient, we are able to capture from this point of view. But of course, we have no real cities. We have urban behavior for consumers, mainly.
Thank you. I would like now to open floor for discussion. Goran was the first one. Can I keep this microphone, and can Anton, we have another one there. Maybe, we have three, but I just need somebody to bring it to the public.
Oh, we can have one of ours.
Yeah.
We have one more. Yeah.
Okay. Can you hear me? Yes. Thank you, Neven, and I would like to thank all the panelists. I have a short question for you. What do you think about nuclear? No, it's a joke. Okay. It's a joke. No. And if you, but your joke with cables is not so, impossible, because I think I like these wires, and it's really simple technology to install and to produce. And if there is any lobby for a wire industry or a grid industry, I think I can work for them, So I think that this is future is in electrification. But I would like to address some of Henrik's, let's say, points. Yeah. If I may be your therapist tonight, I think I know why you don't like optimization, because you get so many of these papers, white shark, gray wolf optimization, etc. So you are maybe a little bit, you don't like them. But if we go to the basics of this optimization, then you will see that they are natural, in nature. So nature is optimizing things, and that's why we should optimize our things. And when we do the simple calculation of thickness of insulation on any pipe, we optimize systems. So we know what is the optimal point, and then we try to reach it as I know what is my optimal weight, and then, I need to lose 20 kilos, so this is something that I need to achieve to be healthy and, to extend my life. But and this is not the point that I want to ask. It's also the comment on the heating energy. So we like to reinvent the heat, and this is what I reinvented when I came to Denmark. And when you show us this very simple pit storages with the solar thermal, etc., which could be expanded in all south of Europe and Ukraine and wherever. It's not complicated technology, and I always ask to myself, okay, if Danish do it and satisfied 40% of heating in small cities and places, we can do even more. And we make calculations, of course, that we didn't get optimal solution because it was always above the price of natural gas. But okay, now it's quite cheaper. But at the end, I just would like to say that, okay, we have a thermal storage and the integration is it's important, but what I would like to say is that you don't need, you need to think about also how it will be produced. So, as I said, if we have solar thermal, we can build gigafactories and produce huge amount of solar thermal, even now help the Ukrainians and everyone with pit storages. This is not difficult technology. But then, when you think about gigafactories, you should also think about the cars, because we have 1.5 billion of cars in the world. How we will drive these cars? It will be electric with the batteries. And now the cost of the battery is 86 euros per kilowatt hour. If how much it will be in 5 years when we will have more cars, when we will have so many gigafactories built in Chile? Okay, this is my final question.
Henrik, can you answer this?
Oh yeah, this is really, really nice. Thank you, Goran, for all these nice questions. Then I can talk for the rest of. No. I know sitting in a room like this with almost only engineers, or at least many, many engineers, and saying skip optimization is like swearing in the church. I realized that, Goran. So maybe I must moderate myself a little bit. And you also said it was strange that I was talking about cost. So I have to specify here myself. I have nothing against identifying technical, liable, and feasible solutions on how to implement the green transition. That is exactly what I'm trying to do. So I have nothing against calculating cost and identifying affordable solutions. That's not the problem. The problem is if I identify 10 affordable solution and learn from that and get wiser, we could do it in this way, and if the PVs decrease in price, we can do it in that way. Then I have get wiser by calculating a lot of affordable solutions by simulation approach and looking at them. My problem is if I put all that into a computer and say, identify the optimal solution, and then I get the optimal solution out and I look at that, and then I don't know all the rest of the solutions. I blind myself into one solution. That's my problem. That's my problem of the optimization process if you apply it on identifying a good future for a country or the world in 20 years' time. So I have nothing against being affordable, technical, liable, good, suitable, whatever, but I have something against ruling out of many solutions that you could not claim that the one is more optimized than the other, that you rule out them and only have one left because you have a computer identifying the optimal solution. That's the problem. That's the problem I'm trying to raise here. And that's why I don't like computer tools that are optimizing and only spitting out one solution. But then, if I should also be fair, most modelers who have a model they call, or a tool they call an optimization tool, actually do a lot of different scenarios. So they calculate many optimal solutions. So then I think it's okay, because then we just have a variety. That's just another way of doing simulations. And that's discussed in that paper I was referring to, and the whole theoretical concept. And I discussed it together with a philosopher and some political science people, because this way of calling it optimal solutions, the one and only and so on, influence how we actually also lead the political debate on what are the assumptions and so on and so forth. And that's why I claim we should have not only one optimal solution, we should present a variety of solutions, because then we get wiser and then we can debate things better. That's my point. Thank you for asking that question, so I could specify that.
I don't know if you're aware, but there are interesting results from La Peranta group, and we have some participants here, so they might want to comment. They have come to conclusion that the most probable best solution to sunbelt areas will be just solar and batteries, because sun is having a periodics of 1 day, doesn't have seasonal change, and batteries will be very cheap. As much as your case of Denmark not predicting the fall of price of batteries has been proven wrong now, not batteries, sorry, solar panels, which are now very cheap. That much batteries, as Goran said, will probably become extremely cheap. We will have many different chemistries, and some of them will not depend on material constraints, so they will be very cheap. Bogdanov, do you want to comment on that? Sure. Yeah, please.
Thank you, Professor Duić, for introduction. Yes, I have a lot of comments on that. And first of all, like we often say that we don't predict the future, we create scenarios. And in this way, any scenario, any solution has its value, because it's one of the possible futures, and more possible futures we analyze, better we know, better we learn as well. And I would also add something in defense of optimization models, and maybe a little bit against simulation, because when we do simulation model, when the researcher does a simulation model, he needs to have some theory how the system should work. So based on that, he has some hypothesis based on his own personal expert opinion or group expert opinion. Then he has several different options, and one of them works. And that's great. But our expert opinion, as of today, is often based on the experience gained from energy system of today. And sometimes it's not good enough to predict the future energy system behavior of the energy system with share of renewables closer to 100%. And when we integrate more and more sectors, when we consider the flexibility of interconnections of these different sectors, we again get in no man's land. We don't have real expert opinion how this will work. And then like design of perfect or very good scenario for simulation model becomes extremely complicated. And then we can create optimization model, feed the data, get some result, and then the most important thing is not to skip detailed analysis of our results. We need to, like, instead of creating scenario based on some theory, we need to understand how the system works, why it made these decisions, why it created this scenario, and what actually made it optimal. And there I see like great value of optimization scenarios, because we may learn from these models how to think out of the box to create new solutions and find new effects which will help to reduce inefficiency of the future energy system. And of course, you're right that optimization models are often very dangerous, because some researcher can simply skip the step of analysis of the result. And then this result doesn't really have significant value. It doesn't develop the science, doesn't provide new clues, etc. Yeah. And I could also add on the perfect work of solar PV in Sunbelt regions. It's one of the solutions which is possible, but which is only possible in case of low-cost PV, low-cost batteries, perfect flexibility of new integrated sectors of transport, industry, etc. But obviously, reality will be most probably slightly different. Government policies will demand more diversified energy supply, and we will see more wind or other sources of energy, and the price will be slightly more expensive. But I think it's valuable to also provide this possible solar-based solution as well.
Thank you for a very interesting comment. Would any of the panelists want to comment on that, or a little bit? Okay. Okay.
I will try to do it short. Thank you very much for the comment, and actually I totally agree with what you're saying. That's also what I'm trying to say here. That is that you can also use an optimization model to do different scenarios, and if you present all of them and don't say that one is optimal and the other is not, then you also become wiser on the different, options. So that is exactly what I'm trying to say. And as you also mentioned, sometimes that computer will lead you into do this type of mistakes. Regarding the analysis of Africa, I will not be in the business here of saying if that is right or wrong. I will much rather join you and understand when is it right and when is it wrong, based on the assumption exactly what you said. One thing that my first question is, does it matter if you include the transport sector? I know there's maybe not a big heating demand. I will expect there will be heating demands for industry anyway, but that's another question. Maybe there are not a lot of heating demand, but there will be a transport demand. And I think that the solution here, at least how many batteries you need, will strongly differ if you do it in a context where you do not include the transport demand compared to a context where you do. Maybe. That will be my first entrance to having a fruitful discussion with you on those results, so we can see when they are useful or not and understand the different options, just as an example. So thank you very much for that input.
Yeah, I think what you said is also important from another perspective. So very often we forget that other countries are at very different development stages. And if you think about the experience in Bangladesh, which is exactly what you are saying, basically millions of roofs with cheap solar PV, small batteries in the homes to provide minimum degree of electricity, which is needed for basic needs. This is happening right now and is basically exploding, particularly in the low-income parts of Bangladesh. I think it shows you that you can use these technologies very differently at different stages of development. It's not to disagree with what we have heard about the integration of transport and heating and so on, but I think exactly those type of solutions are useful in this very early development stages, where people can afford a few appliances and the minimum level of electricity.
Shir, did you want also to comment on that?
Yes, I would like
okay.
I would like to add to the discussion.
Which one is that?
Yes.
Sit down.
Just adding to the discussion, I wanted to emphasize that capturing synergies is also very important, because there's an implementation gap that we're trying to provide the modeling and the model scenarios to support us in providing us the insight, so how we can close the implementation gap. And when that comes into play, one of the synergies that become important or co-benefits, how can we couple the results of our scenarios to the co-benefits? A report released just today, just before coming to this panel, indicated that right now in the renewable energy sector we have 13.7 million jobs, and this is increasing by 1 million from previous year. And if you compare it with the previous years, even 7.3 million in the most recent years have been created in the renewable energy sector. Some of the technologies that we have there are per unit energy, providing some of the most number of jobs. If the countries do have the manufacturing capabilities, then this can directly translate into the job opportunities that they can capture in their local areas. So I think that when we look multidimensionally and trying to motivate how we can close the implementation gap, coupling our results with possible co-benefits that can be reached, or if the co-benefits do not provide sufficient motivation, then perhaps seeing the trade-offs could also motivate how can I increase these job opportunities to be captured in my local area. So whatever is the optimized result or simulated results, we also need to be mindful of how we can provide insight to help us close the implementation gap.
Thank you. So we had a question here, Birol? Comment, okay. Please, Anton.
Thank you. If I may go back to the optimization versus simulation situation, it seems quite strange to me why we put optimization against simulation or vice versa. Optimization involves in its every step simulation. Without simulation, you cannot optimize. In my 50 years of optimization history in scientific field, I have never done any project just spitting out a number or picking a number from the computer. It's a human-machine interface, a dynamic case where you actually digitally talk with the computer. It computes something to you. If you like it, you proceed into the next step with a new simulation or some alterations. So it's a joint process. It's a one process in one package, optimization and simulation. So we cannot differentiate them. And I would therefore suggest that we should come to a solution that optimization is necessary because it goes hands in hand with simulations in its every step, like in a steepest descent method. You go to the optimal, but at every step you change something, and that change means simulation, another simulation. Thank you.
Thank you. I think the comment was self-contained and that doesn't need answering, but there was a question from Michael, and then Natasha.
I think I travelled the furthest to get here, and 250 years ago, Captain Cook sailed to New Zealand using renewable energy. But I flew here, and my carbon footprint went through the roof. Now, I've sat here for almost 4 days, and very few people are talking about aviation. There was a bit on shipping. Now, New Zealand has about 10% of its energy system is on international fuels for transport, and it doesn't even appear on any government reports. I had to dig it out and put it into a paper to cause a bit of a controversy. So some countries are closing their eyes to international transport fuels because I don't know if they're counted yet. So what's the view of the panel about the need for that to start being counted and to sort of force us to start seriously doing something?
Shall we have IPCC guys or Henrik? Okay, Henrik is the first one. Short answer.
I will try to make it short again, but I know that you saw my presentation. And I did include international aviation and shipping. And just to linking to the discussion we have here, and I will not say anything about simulation or optimization or anything like that, but just to linking the discussion we have here is that the point of that presentation I made when you were there was actually when we include that is a major part of the system, then what we discuss here now, the integration of wind and PV becomes much more doable because we simply have to use much more electrolysis, to put it very simple and short, and then we have much more flexibility into the system, not for the reason of the wind turbines and the PV, but for the reason of the international aviation and shipping. And then, because we need the electrolysis to do that, then we put in the option of storing the wind and the PV without further loss in energy efficiency than the one that is connected to decarbonizing the transport sector, then we induce the option of storing the wind and PV much more affordable in the gas and liquid fuel storages.
And one can already buy synthetic e-fuels only 5 times more expensive than the mineral ones. So with learning curves, we can do it. Natasha, or if anybody wanted to comment, but I think Henrik's answer was good. Please.
Okay. First of all, question for Henrik. If we are so sure that smart energy systems are the key concept for decarbonization, why do we put so much effort maybe to develop so many integrated assessment models and stories? Why maybe to put more efforts in generating good case studies at national level and local level and exchange these best practices, maybe to go and to facilitate decarbonization bottom up, not stemming out from global scenarios, I would say. This is the first question. And the second question is maybe for IPCC people. It's, okay, if we are sure, and we have, as energy modelers, very strong models which will generate very, how to say, robust mitigation pathways with achieving 100% renewables goals and Paris Agreement goals. Then we could, why don't we go vice versa and put our additional efforts to extend our models and to increase these dimensions of socioeconomic, you mentioned integration of sectors, but sectors, emitting sectors. But here we also consider a lot of other sectors from economy, from society, from environment. Maybe step ahead would be to go vice versa and try to do extension of our models to make them integrated in order to produce also answers which I would say economically oriented, social oriented, environmentally oriented questions can be also answered. Because going with this, you mentioned at the very beginning, we had very robust and trustworthy mitigation pathways even with earliest assessment reports. And not much happened. Now the stock-taking reports have shown that we are far away of reaching the goals. So it means that having this much complexity in the integrated assessment, introducing, we produce some scenarios which might in a way defer mitigation. For example, in some countries where we have strategies for phasing out of coals, we start talking about carbon capture and storage or hydrogen instead of taking decisive actions for phasing out of, for closing the coal power plants. So maybe going in this direction would be a better approach. I don't know. I would like to hear your opinion about that.
Who's going to answer this? The last one or the first one? The last one. I'll maybe start with the last one and then we'll go with the first one. Okay. Please.
Yeah. So I think that's a development which is taking place as we speak. Yeah. So to try to integrate other societal objectives than climate mitigation in the modeling, not only in the integrated assessment modeling, the global one, but also I think you need to do it particularly at the local scale, because these trade-offs of different technologies look at the local scale quite different, right? So that's one of the, can you hear me? Yeah. That's one of the decisive things that one needs to understand is that the portfolio of technologies that at the end will deploy will depend on the local trade-offs that you have. In some circumstances, you might have a lot of biomass. You don't want to go X to power in that circumstance. You might gasify biomass. And in other circumstances, if you have abundant solar. I just was in Israel last month, and we have discussed the Israeli energy strategy, and with their solar potential, it would be crazy not to go massively into that direction. But I wanted to come back to your coal comment. So if there is one thing that is really coming out of the IPCC very, very strongly is that we have to immediately stop to invest into coal power generation, and that we have to prematurely shut down coal power plants which are running at the moment. Yeah, I have the impression it's going up and down, or is it just me? Perhaps. Yeah. So this is. I think what is the strength that is coming out from the IPCC assessment is that it shows you the trade-offs of following different pathways. Yeah. So the key conclusion, I think, from the AR6 assessment is the big power of limiting the size of the system. So basically changing the demand side, improving efficiency, limiting the amount of energy that we use, has this double dividend that any renewable that you contribute actually really increases. You can increase the share of the renewables much quicker. Yeah, and it shows also what are the differences between a future scenario that focuses a lot on CCS, very heavy, big infrastructure, very technocratic way of solving the problem, compared to very rapid and accelerated change if you focus on granular and small-scale technology. So a lot of that, what you actually said, that we should look into, I would argue some of it is already in the report itself. What we all as a community need to improve is we need to understand, we need to get away from this single objective climate. We need to understand climate compared to all other societal objectives, and prioritize the mitigation options not only in terms of the dollar per ton of carbon, but also in terms of the service that they provide for other things. Like mobility. Mobility switch might be much more attractive because of getting rid of congestion in cities, basically more convenient traveling if you don't have to travel yourself in a car, and all those type of co-benefits that usually, which is actually difficult to get into our models because they are so energy and material focused at the end.
Thank you. Now all microphones have disappeared, so I have to share this one. Shiri wanted to comment on the second question, and then pass it to Henrik to comment on the first question, and also try to do the very short and final statements included, because we have to slowly close the panel.
I would like to once again emphasize the cities and urban systems, because it's also not only where the energy is concentrated, where the infrastructure is concentrated, but also where the people is concentrated, and therefore where the co-benefits can be most valuable to the people. When there's a switch in the energy supply, the improvements to air quality. It's very important that the results are coupled to such co-benefits, because it is motivating ways that we can close the implementation gap. Also, the connections with the SDGs, because we're not on target to reaching the SDGs, how some of the mitigation options could support the ways for co-achievement of mitigation and sustainable development. And maybe perhaps ending with another importance for sustainable development pathways, it would be to how mitigation options can also support adaptation and vice versa, and seeing the linkages, because in a connected world and a connected reality, we also need to see that climate is connected, our well-being is connected to climate, and at the same time, we have to be clear in communicating that this is for our planet, this is for the people, and this is for our climate future. Thank you.
Thank you. Henrik.
Yes, I started my presentation by saying that if a model is good or bad, or how many models you or we all together need, depend on the topic of our study and what we try to answer. So I think it's good we have lots of models. including optimization models, so we can answer different things. And also, I think it's good to have competing models, also for the reason you said that, of course, the model I have made is reflected in how I view the world and my theories behind it and so on. And for that reason, I think it's good to have a variety of models. But coming back to what I also said is, in the way I see the world and experienced it, and my personal theoretical view on this is that I can find better and more doable and more affordable solutions to today's topic of integrating wind and solar and variable renewable energy if I generate a context of looking at all the sectors in a coherency compared to if I don't do that. That's why I am in favor of a model that can show that and can calculate that. That's why I argue under the name of the smart energy system, because then I can show that and discuss that. And then maybe I have not included enough sectors, as also mentioned here. There are many other sectors also. So of course, we can all do better also in the future. I think that's also a takeaway from this meeting here. But it's because I see the world as I do, and it's because I wish to investigate what I wish to investigate that I use a model that is suitable for that.
Thank you. Luis, would you like to have a final statement? No? Okay, Felipe?
Can you hear me? Yeah. So just to finish, I want to address, I'm going to finish addressing the last comment of Natasha about why not going beyond in the energy system models that we develop. So I truly agree with Natasha. So I think as a scientists and energy system modelers, when we develop H2S or energy plan or LUT model, any model, we put boundaries. And the boundaries are basically in this energy system. And we are forgetting that there is, 30% other emissions coming from different sectors, not only from the energy system. So we need to break the box and go beyond the energy system. And that's one of the wonderful things that EAMs can actually allow us to do. So for instance, we show in one of the slides, when we try to look into the NDCs, we try to basically being carbon neutral. We always care about what is the price of electricity, dollars per megawatt hours. But we never talk about what is the price of food, for instance. What is, how many dollars per tons of food? We always, we get scared. We say, oh, electricity prices will go 10% higher or 20% higher. But we show that if we meet the NDCs or we are carbon neutral, at least in the Latin American context, food prices will go up 15 to 20%. So why don't we talk about that? We don't talk about that in this community because we only focus on energy systems. But we really need to go beyond that. So that's basically addressing Natasha's question. I think in H2S, and I said in the Inter-Energy panel, we should maybe look into the synergies between energy and how biomass is produced, or how land use is basically used based on the solutions that are coming from H2S. So I think there is a long way forward, basically to include, or maybe, let's say, improve basically what we do in energy system planning.
Thank you. So what I think that we have concluded tonight is that we are not predicting future. We are just trying to find out what will certain decisions bring as a consequence. So any of the models we use will give us a certain level of insight, and none of them will solve all the issues. There is no perfect solution. I would like to thank you all for this excellent panel. Thank you very much. Thank you.